Hey everybody, so we are to chapter 9, and we're going to continue kind of the idea of chapter 8, but we're going to be dealing with two proportions and comparing them to one another. Chapter 9 does two proportions, then two means, then standard deviations, and we'll just go ahead and get started. So this is anytime we want to compare one group to another group to see if they're the same or if they're not the same. And one of the requirements is it's got to be simple random samples and that they are independent of one another, meaning that the two samples that are collected need to be completely isolated from one another so that there's no contamination. In addition to that, we need that n times p hat is bigger than or equal to 5, and n times q hat is also bigger than or equal to 5. And again, that has to do with the population size and things like that. So let's move on to the test statistic for two proportions. And our null hypothesis is always going to be that one proportion is the same as the other proportion. And this will translate for us to mean in our calculators we're going to be using a two proportion z-test. And I'll show you where that is in the calculator in just a minute. It's actually where all the other tests are, under stat. Our formula that we will be using, this is our test statistic, is going to be p hat sub 1 minus p hat sub 2 minus p sub 1 minus p sub 2. Now, just again real quick before I even finish this, these are the sample proportions from the two populations. These are the actual proportions that we are assuming are the same, so that actually goes to 0. If they're equal, you can see that that's going to be the same minus the same, so that'll go to 0. Now the denominator is going to use a bunch of different things, so I'm going to have to be very careful. This is going to be p bar times q bar over n sub 1, and I'll define those in just a moment, plus p bar times q bar over n sub 2. So real quick, let's do some definitions here. We have p hat is x sub 1 is x sub 1 over n sub 1, and p hat sub 2 is x sub 2 over n sub 2. And we have our p bar, and we're going to be pooling these together. So this is sort of the mean, or proportion in a way, pardon me. And of course, q bar is 1 minus p bar. And this is what's called a pooled sample proportion. And well, I won't get too deep in what that means. It just means we're combining up the two to make them sort of one big sample, as it were, in a way. And here's our practice. Let's push that up there. And we have a study of police gunfire reports during a recent year. It was found that among 540 shots fired by the New York PD, 182 hit their targets, and of the 283 shots fired by LAPD, 77 hit their targets. And we want to use a 0.05, so we have our alpha. Significance level to test a claim that NYPD and LAPD have the same proportion of hits. And so our null hypothesis is, again, P1 equals P2. And our alternative hypothesis is that they're not the same. So we are going to be dealing with a two-tailed test here. And so here we have two-tailed means that we take the alpha and cut it in half. And from previous ones, that means that, well, I'll write it out, or I'll show you how we get that. So once again, we want inverse norm 0.025 will give me the left one. That'll give me this one here. And you can see it's a negative 1.96. And if we did the other, I can show you, 1 minus 0.025 gives me a positive 1.96 as well. To find our test statistic, I actually can go in to a new test. So we're going to go stat tests. And once again, this is a two-prop, pushed it too high, two-prop z-test. And you can see here's our two-prop z-test. And x sub 1, it looks like, is 182. So New York is going to be my sub 1, as it were, out of 540. X sub 2 is going to be the 77 out of the 283. Again, you can read the original problem as you look at that. And then P sub 1 is going to be not equal to. And we are going to calculate in very nicely our test statistic. Is going to be that we have z equals 1.91, I'll say, rounded off, with a p-value of 0.057, we'll say, rounding it off. Now this is to be compared to, this is definitely bigger than our alpha, which is 0.05. So just to be clear, 1.91 is there. And of course, this area is half that, because we have also over here. So this value here is 1.91. It's just shy. So it's looking to me that we are in the fail to reject zone. The null hypothesis. Because the critical value, or I guess we could do the p-value method, the p-value is larger than the critical value, the alpha. And so that means that we fail to reject it, so there is not sufficient evidence. Now, this technically isn't right. The claim is actually here, but I'm forcing the claim to be here. I'm asking sort of a different question. I'm saying that there's a claim that they are different. So I'm changing the claim from this original problem here, because we would have to word this last part a little bit differently. There's not sufficient evidence to support the claim, and again, I've moved the claim a little bit to be the alternative hypothesis that the proportions are not the same. There's our first example. So we are going to construct a confidence interval. So we're sort of just kind of combining everything up here. What we're constructing is a confidence interval between the difference between the two proportions. And we want to think that 0 is in there, and that'll come into play here in just a moment. So technically, our confidence interval looks like this. And E is defined here. C sub alpha over 2, P hat sub 1, Q hat sub 1 over N sub 1 plus P p hat sub 2 q hat sub 2 over n sub 2. And then very nicely, of course, our calculator does all this work for us. So let me show you where we're going to do that. We're going to look up, this is a 2-prop z interval, confidence interval. So we have the same idea here. So this is just, we can do the testing like we did here. So it's the same question, but now we're going to use a confidence interval to determine if the proportions are the same or not. So we have the same null hypothesis and so on. And I'm going to go to stat again, tests. We're going to go to 2-prop z interval, this one here. And it actually saved it from the previous problem, so it actually has everything still in there. It needs to know the significance level, so the C level is 0.95, and you can see because alpha is 0.05, our C level is 0.95. So it's whatever makes up the 100% there. And what we're going to end up with, we can see, is a very, very small number. So here's our confidence interval. So the main thing that we're looking at here is the fact that we go from a negative to a positive. And what that means for us is that 0 is in here somewhere. So 0 is within the boundaries. And so we could still come to the same conclusion. If it was outside the boundaries, then we would reject the null hypothesis, but we're going to fail to reject it again. And once again, that is the same conclusion that we came to on this one as well. And rightly so, it's all the same data, it should all jive. And the same significance level has to be held as well. So we're going to try this next one. And this time I'm not going to use the confidence level. I'm going to use the test again. And let me mark this up just a little bit. So among the 58,593 patients who had a heart attack during the day, so this is my x sub 1 and this is my n sub 1. And this is my n sub 2 and this is my x sub 2. And so once again, I'm going to go to tests 2-prop z test. So I'm going to put my data in. So 11,604 of the 58,593 and 4,139 out of the 28,155. And overall, this is comparing. And once again, let's do this. So this is once again a two-tail test. And we have different significance levels, so let's actually draw this out. We have to split it up into two pieces here. And to find that critical value, we'll come back to that. We have to do inverse norm, 0.005. That'll give me the left one, the negative one here. And you can see that's a negative 2.58, we'll say, and that'll make that a 2.58. Again, I can show you where that comes from. inverse norm 1 minus 0.005. So there it is. So I'm now going to run the test, stat test 2 prop z test. I have all the data still in there, and calculate, and it gives us that z is out here, way out here. If this is 2.58, 18 is way out here. So we have a z is 18.26, which is ridiculous. And our p-value, my calculator and yours might be different. It depends how far out it goes. Mine in particular says 1.8 times 10 to the negative 74th power. Some of yours may say 0. Some of you may have different numbers with maybe a different magnitude. The point is, it's about 0. I want to do the confidence interval as well, just to show us. So 2 prop z interval, and it still has all the same data in there. We have a different C level in this case, 0.99. And you can see we are not going from a negative to a positive, so 0 is not in there. So either way, however you want to interpret it, we are going to reject the null hypothesis. This means, and again, I'm forcing, even though, however it's worded, I'm forcing this to be the claim. And on a test or something, you can make the same assumption. So there is sufficient evidence. To support the claim. That patients die more at night. I shouldn't word it that way. Die unequally from day to night. I hope that was helpful. Make sure you